All right, diving right in. It looks like we've got a pretty fascinating topic on our hands today. Based on what you've sent over all these articles, reports, it's clear you're really keyed into something pretty important here. Rare earth elements. They're kind of the unsung heroes, right? Powering so much of the tech we rely on every day.
Yeah, exactly. Not always front and center, but absolutely essential.
So for this session, we're going to, well, take that deep dive, really extract what you need to know about rare earths. And of course, a big part of that story, as your sources highlight, is China's pretty powerful position in the global market. We want to give you that solid understanding without getting bogged down.
Absolutely. I think your sources do a great job of zeroing in on those key areas, understanding what rare earths are, getting a handle on China's influence, and then seeing how that all fits within this larger global industry. It's a complex landscape for sure.
Definitely. So let's start right at the beginning. What are we actually talking about when we say rare earth elements? What exactly defines this group?
Sure. So basically, we're talking about a collection of 17 metallic elements on the periodic table. And within that, there are the 15 lanthanides. Those are the elements with atomic numbers 57 to 71. Now, that whole group, the lanthanides, they share certain electronic characteristics, and that's what gives them these unique properties that we're going to talk about. Then, along with those 15, we include scandium and yttrium. They're not technically lanthanides, but they behave in a similar way, chemically speaking, and they're often found together, in the same mineral deposits.
Okay, 17 elements total. But I gotta say, that name, rare earth, can be kind of misleading, right? It makes them sound incredibly scarce.
Right. It definitely does. And that's one of the biggest misunderstandings about them. They're not actually all that rare, at least not in terms of their overall abundance in the Earth's crust, like cerium. It's about as common as copper. And then you've got praseodymium, which is even more abundant than lead. The rare part comes from the way they're distributed. Instead of being concentrated in these easily extractable deposits, they tend to be scattered around, often in pretty low concentrations.
Ah, so it's more about how easy they are to get at, not so much about their overall quantity.
Exactly. Imagine trying to collect tiny specks of gold dust scattered across a beach versus finding a big gold nugget you can just pick up. That kind of sums it up.
That's a great analogy. Now, within these 17 elements, are there further distinctions? Do they fall into different categories or anything like that?
Yeah, so we usually group them into what are called light rare earth elements, LREs, and then heavy rare elements, the HREs. Now, the LREs, that typically includes lanthanum, cerium, praseodymium, neodymium, samarium, europium, and gadolinium. These tend to be used in more large-scale applications, I guess you could say. And then the HREs, those are terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium, along with scandium and yttrium. You might see slightly different classifications depending on where you're looking, but that's the general idea. The heavier ones often go into these high-performance magnets, the kind you'd find in smaller, more compact devices.
Light and heavy, got it. But what is it about these elements, chemically speaking, that makes them so vital for so much modern technology? What are their sort of standout properties?
Well, it all boils down to their unique electron structure, especially the way their 4f electron orbital is filled. This gives them these really strong magnetic properties, phosphorescent properties, and catalytic properties that you just don't see in a lot of other elements.
Mm.
It's really this unusual atomic setup that makes them so versatile for all these different high-tech applications.
So it's all about how those electrons are arranged. Okay, let's talk about some of those applications. Where do we actually encounter rare earth elements in our daily lives?
Well, one of the most important areas is in permanent magnets, particularly those made with neodymium, iron, and boron, the ND-Fe magnets. These are the most powerful permanent magnets we have right now. I mean, they're about 18 times stronger than a typical iron magnet of the same size. And you find them everywhere, from giant wind turbines, which can use hundreds of kilograms of these magnets in a single unit, to the motors in electric vehicles, hard disk drives in computers. They rely on these incredibly precise read-write heads, even the speakers in your audio equipment. Then you have samarium cobalt magnets, which are really good for applications where they need to withstand high temperatures.
18 times stronger than iron magnets. That's hard to wrap your head around. Where else do they pop up?
Well, they also play a crucial role as catalysts, which are these substances that speed up chemical reactions. For instance, lanthanum is used heavily in petroleum refining. It's part of this process called fluid catalytic cracking. And then cerium, that's really important in catalytic converters for cars. Those things that help clean up exhaust emissions.
So basically, they're helping reduce pollution, which is great. What about in those more visually striking applications like screens and lights and things like that?
Absolutely. Rare earths are essential for creating these luminescent materials, the things that make things glow. You've got europium, terbium, and yttrium. These are used as phosphors to produce those vivid, accurate colors in LEDs and displays. Your LCD TVs, your smartphone screens. That's all thanks to rare earth elements. They're also used in fluorescent powders and in various laser technologies, like erbium is crucial for fiber optic amplifiers. These help boost signals over long distances, which is essential for, well, the internet as we know it. Then there are erbium-doped YA lasers used in surgery and neodymium-doped YA lasers. They're used in manufacturing and medicine and even in some military tech.
Wow, so from lasers to vibrant screens, they really are everywhere. What are some other maybe less obvious places where they're used?
Yeah, well, they're actually used as additives in glass to enhance its optical properties. For example, lanthanum is used in making high-quality camera lenses, even the ones in your smartphone. It helps make those images sharper and clearer. They're also used to improve fiber optic cables, which are crucial for data transmission.
So even the tiny lens in our phone uses these elements. That's pretty wild. I know we're seeing a huge shift towards electric vehicles and renewable energy. Do rare earth elements play a role in battery technology at all?
Yeah, definitely. Lanthanum is a key component in nickel metal hydride batteries. You still find those in some hybrid vehicles. And both lanthanum and cerium are used in lithium-ion batteries. Those are the dominant type in EVs and tons of other devices. They help make them more stable, last longer, and perform better overall.
It's really incredible the range of applications from these tiny components to large-scale energy infrastructure. And I know from what you sent, they're also essential for defense, right?
Yeah, that's a big one. They're used in all sorts of defense applications.
Yeah.
Precision guidance systems for missiles, radar and sonar systems, night vision devices. They really provide a technological edge. And specific elements, like scandium and yttrium, have very specialized uses in various advanced defense technologies.
Okay, so we've established just how crucial rare earths are. Let's shift gears now and talk about something that came up a lot in the material you sent, and that's China's really significant dominance in this global market.
Yeah, China holds a really strong position in the rare earth market for several interconnected reasons. First off, they just have a lot of natural resources. They're estimated to have about 37% of the world's known reserves. Now, their control over total global supply has actually decreased from its peak, which was over 90%, but they still account for the biggest chunk of production and are the main exporter.
So it's not just about having a lot in the ground. It seems like they made some strategic decisions early on that really shaped things.
Absolutely. Way back in the 1980s, the Chinese government recognized the strategic importance of rare earths and invested heavily in developing their mining industry. But crucially, they also invested in processing technologies. There's that famous quote from Deng Xiaoping, "The Middle East has oil, China has rare earth." That really sums up their foresight.
They weren't just thinking about digging it up. They had a much broader vision. And it sounds like they've built a much more vertically integrated industry than other countries.
Exactly. China developed this complete industrial chain, from mining the raw ores all the way to manufacturing finished products like those ND-FePi magnets we talked about. This means they have the capability to do the complex separation, refining, and alloy production, the whole shebang. It's a huge advantage that other countries have struggled to match. To put it into perspective, they currently control about 83% of global refining capacity. And there are projections that suggest this could reach 90% by 2040. So it's not just about raw materials, it's about control over the processing know-how. That's what really sets them apart.
So even if other countries find more deposits and start mining more, they still have to overcome this technological hurdle of processing. Your sources also talked about the role of government policies in China's dominance.
Right, the Chinese government has been very strategic. They've used a variety of policy tools to control the industry. This includes things like implementing export quotas, setting production limits, and encouraging consolidation within the industry. This has often led to the formation of these large state-backed companies, like the China Rare Earth Group. Then there was the 2010 incident with Japan over the Senkaku-Ryu Islands. China restricted rare earth exports to Japan, and that really brought the issue of supply security to the forefront globally. Although official quotas have been lifted since then, China still has other controls in place, like they have quotas on mining, smelting, and separation, and they have these systems in place for tracing rare earth products that are exported. More recently, they've also imposed export controls on specific rare earth elements and related technologies.
So that 2010 situation was a real wake-up call for a lot of countries. It showed just how reliant the world had become on one supplier. There was also some talk in your sources about environmental factors playing a role, at least historically.
Yeah, it is true that historically China had less stringent environmental regulations, which contributed to lower production costs. But it's important to understand that this is changing. China is now tightening environmental controls due to the serious environmental impact of mining and processing. There's a lot of toxic waste generated, including radioactive materials like thorium, so those cost advantages related to environmental regulations, they're shrinking.
Interesting. So the playing field is leveling out a bit on that front. Now let's zoom out and look at the global picture beyond China. Where do other countries fit into this?
While China is the dominant player, there are rare earth resources scattered across the globe. Significant reserves exist in the USA, for example. The Mountain Pass mine in California, which restarted operations in 2011, is a major one. Australia has the Mount Weld mine, operated by Lannis. And there are reserves in Myanmar, Vietnam, Russia, India, Brazil, and Canada. Canada actually has over 15 million tons of estimated reserves. There's even potential in those deep-sea mud deposits near Japan. And new potential mining areas are being explored in the U.S., like in Wyoming, Arizona, and the Southern Appalachian Basin. And Greenland has massive untapped reserves. The thing is, a lot of these countries with significant reserves, they just don't have the processing and refining capabilities yet.
So it's one thing to have the raw materials, but you need that infrastructure and know how to turn them into something usable. Your sources talked about this three-stage industry chain: upstream, midstream, and downstream. Can you break those down for us?
Sure. So the upstream stage is all about the initial mining and processing of those raw ores. You've got to extract the ore from the ground, sort it to concentrate the valuable minerals, and then use techniques like acid or alkali leaching to create that initial extract. Now, this stage can have a big environmental impact, especially with potential contamination from radioactive elements like thorium, which often occurs naturally alongside rare earth minerals.
It sounds like a pretty tough and potentially messy first step. What happens next?
That's where the midstream comes in. This is where we get into separating and refining the individual rare earth elements. And this is where it gets really tricky. Because they all have such similar chemical properties, separating them is a complex and expensive process. It involves multiple steps to isolate each element, refine them into oxides, reduce them into pure metals, and then create those different alloys. And as we've discussed, China is way ahead in this area. They have the technology and the expertise, and that's a major barrier for other countries trying to catch up.
So even if other countries ramp up their mining, they still have this technological hurdle to clear. And then we have the downstream stage.
Right. The downstream stage is all about turning those refined materials into usable products. This is where you have the manufacturing of permanent magnets, the production of luminescent materials for screens and lighting, the creation of catalysts for various industries, and finally it's about incorporating all those components into the end products we use, or electric vehicles, wind turbines, electronics, all of that.
Yeah.
And what's really interesting is that even the manufacturing of a lot of those high-tech products that rely on rare earths, that's also concentrated in Asia, especially in China. So it gives them even more influence.
So there are multiple points of vulnerability in this global supply chain, and it seems like the processing, that midstream stage, that's a major bottleneck.
Exactly. The fact that so much relies on one geographical source, China, is a big vulnerability. And then you have those high technological barriers to entry in that midstream processing, which gives China a significant advantage. The environmental and social challenges of mining and processing rare earths can also make other countries hesitant to develop their own industries. And then, like we said, the concentration of manufacturing in Asia just reinforces China's strong position.
So given all of that, what are other countries doing to address this situation? What strategies are they using?
Well, they're taking a multi-pronged approach. Supply diversification is a big one. That means reopening mines that have been shut down, like the Mountain Pass mine in the U.S., and developing new mining resources in places like Australia and Canada. There's even exploration of less conventional sources, like those seabed mineral deposits and urban mining, which basically means recycling. And then there's technological innovation. This is all about developing alternative materials to reduce our reliance on certain rare earths and finding ways to improve recycling and reuse. Still early days for a lot of that, but there are initiatives like the EU's Sisan Magpro project that are pushing things forward.
Recycling does seem like an area with huge potential. What other strategic responses are we seeing?
Well, countries are building up strategic reserves of rare earth elements and forming alliances to help ensure a more secure supply. And of course, government support is crucial. This includes financial incentives for domestic industries, stronger trade partnerships with allies, and setting up international mechanisms for coordinating all these efforts.
It sounds like a really complex challenge with no easy solutions. What does the future hold for the rare earth market? I'm guessing demand is only going to increase.
That's right. Global demand is projected to keep rising, mainly because of the shift towards green technologies and the fact that everything is becoming increasingly digital. We could see a 30% to 50% increase in demand by 2030. And the demand for certain elements like neodymium and praseodymium, those are crucial for those powerful magnets used in wind turbines and EVs. That demand could double between 2020 and 2030.
That's a huge increase. What about the supply side? Do we expect to see more diversification away from China?
We'll definitely see an uptick in production from other countries, but dislodging China from its dominant position, especially in processing, that's going to take a long time. It could be 10 or even 15 years before the West can establish truly independent supply chains. We're seeing more interest in new mining areas, like those in Greenland, Myanmar, and Vietnam. But realistically, China is just so far ahead that a complete decoupling in the near future is unlikely. That's why strategic partnerships and technological innovation are so important.
And what about the environmental side of things? Will that continue to be a major factor going forward?
Absolutely. The push for a circular economy means we'll see more focus on recycling and reuse. Right now, most of the recycling efforts are focused on production scrap, and China's recycling rate is around 16%. But other places, like the EU, are trying to catch up. Plus, the global industry is going to face stricter environmental regulations, which will push the development of cleaner production technologies.
So it seems like we're at a critical point in this whole story. And with rare earths being so vital, geopolitics must factor in heavily.
For sure. Rare earths are a key piece of the international power dynamic. We're already seeing this playing out in the way global supply chains are being restructured. And we're also likely to see more technological innovation with the development of substitutes that reduce reliance on certain rare earths. But there's still a long way to go in that area.
Some of the materials you shared also pointed to some recent moves by China that suggest they're tightening their grip on the rare earth supply chain even further.
Yes. Since October of 2024, China started requiring exporters to provide very detailed information about how their rare earth products are being used. Basically, they want to know exactly where their products are ending up in Western supply chains. This gives the Chinese government a lot more visibility and control over who has access to these materials. We've also seen an increase in state ownership of companies within the Chinese rare earth industry, with foreign-owned companies being bought up by state-owned enterprises. And they're controlling information more tightly, too. Rare earth mining and smelting are now classified as state secrets, and there have been cases of people being punished for sharing information with foreigners. And it's not just rare earths. They've extended these controls to other materials like antimony, gallium, and germanium.
So that incident with Japan back in 2010 really highlighted the geopolitical aspect of this whole thing.
Right. When China restricted exports to Japan during that territorial dispute, it really showed how they could use rare earths as leverage. And that really got other countries thinking about their own vulnerabilities.
And those concerns are only growing based on some of the statements from world leaders and industry experts that you highlighted.
Exactly. In 2024, the White House released a statement specifically calling out China's near monopoly on rare earths as a major risk to global supply chains. And experts have been using some pretty stark imagery to describe the situation, like comparing it to a Damocles sword hanging over key industries.
So that's a pretty tense situation. To wrap things up, it seems like the US, Australia, the EU, and Japan are all trying to counter China's dominance in their own ways.
Yes. The U.S. is focused on boosting domestic mining and working with allies like Australia and Canada to create more secure, non-Chinese supply chains. They're also using financial incentives to encourage domestic production. Australia is also pushing ahead with developing its own rare earth projects. The EU is promoting this idea of friendshoring, which is about working with friendly countries to build more resilient supply chains. And Japan, having experienced the consequences of supply disruptions firsthand, is diversifying its sources and investing in recycling technologies.
Your sources also included some interesting case studies of major rare earth mining areas in China, like the Bayan Obo mine.
Right, the Bayan Obo mine in Inner Mongolia is a really important one. It was originally discovered as an iron ore deposit in 1927, but then they found out it was also the world's largest rare earth mine. It contains a huge amount of the world's reserves, especially those lighter rare earth elements. The Baogang Group runs it. The mine does have a lot of environmental challenges associated with it, though, and it's interesting. They recently discovered some new heavy rare earth minerals there, too. This new find, they call it Bayan Obo Mine U ore, And it just shows how important that site continues to be.
And then there are those ion adsorption clay deposits in southern China, right? Those are important for a different reason, aren't they?
Yes, those deposits, found mostly in the provinces of Jiangxi, Guangdong, and Fujian, they're the main source of heavy rare earths globally. They were formed when granite weathered over time, and rare earth ions got trapped on the surface of clay minerals. They often extract these rare earths using a technique called in situ leaching, which can have some environmental drawbacks too. But the point is, China's control over those deposits is really critical for the global supply of those heavy rare earth elements, which are essential for all sorts of high-tech applications.
Well, it's clear that rare earth elements are absolutely essential to our modern world, and China's dominance in this market creates a whole host of complex issues, both economic and geopolitical. Understanding these dynamics is crucial for anyone who wants to understand where technology and global trade are headed.
Couldn't agree more. You now have a really good foundation to understand not just how important rare earths are, but also all the factors that go into China's position, the global strategies at play, and just how intricate this whole industry is. Hopefully, this deep dive has given you a much clearer picture of this complex landscape.
Absolutely. And on that note, here's a final thought for you to chew on. We know that the demand for green technologies is only going up, and these technologies rely heavily on rare earth elements. So, given everything we've talked about, what do you think will happen? Will these efforts to diversify supply chains be enough to shift the balance away from China? Or will we see the emergence of new technologies and materials that reduce our dependence on rare earths altogether? It's a really fascinating question to consider, especially when you think about the interplay between economic growth, protecting the environment, and ensuring a stable supply of these essential materials. Thanks for joining us for this deep dive.